All right, we're looking at 10.7, special segments and circles. So we've actually learned a couple different properties of some special segments and circles. For instance, just draw one. So we know, for instance, that if we have a tangent line and another tangent line coming from the same exterior point, we learned that these are congruent, right? So that's a special segments property. What else did we learn? So we also learned if we have a tangent line and then we have a radius drawn to that tangent line, that is always a 90-degree angle. So there's another special segment. So we're going to learn more about stuff like this, secant lines, tangent lines, and the relationship and the segments that they make. So let's take a look at our first one here. So let's read this together. It says, if two chords intersect in a circle, then the products of the lengths of the chord segments are equal. All right, so I color coordinated this. You can do the same. What it's saying is if you've got two chords intersecting, then this part AB times this part BC is equal to this part DB times this part BE. Pretty simple. Now, when I first looked at this, I was like, I mean, it made sense, but I'm like, well, why is that? So I kind of jotted out a proof for this, and it's actually really logical, and it's not very long, so I wanted to take you through it real quick. I proved this thing in 5 simple steps. You could actually do this yourself. So let me show you real quick. Here's the proof. I basically drew out the same picture as the above circle, so you guys have that in your notes. You don't have to write the proof down. I just want you to follow along with me here. All right, so here's my picture. I'm going to prove that this times this equals that times that. Now, I started with a given statement. All right, so from my picture, I can say that AC and DE intersect at point B because that's given to me. I drew that picture. Okay. Step 2 here. I said that angle A has to be congruent to angle D. So I can mark those. Reason why, first of all, I'll stop it there. Take a look at angle A. That's an inscribed angle, right? Boom, you got an inscribed angle here. And same with angle D, it's inscribed. And they have the exact same endpoints, which means there's a theorem that we talked about in the inscribed angles section. If they have the same endpoints, then those angle measurements have to be the same. Okay, so those are congruent. Also, angle E is congruent to angle C for the exact same reason. E and C, right? Those are both inscribed angles with the same endpoints. So that would be my reason. Inscribed angles that intercept the same arc are congruent. All right, so I know that much. From there, and this is something you guys learned about in, gosh, I don't know, several chapters ago, but it was the triangle similarity chapter. So because of what we marked here about the angles being congruent, we can say that triangle ABE over here is similar to triangle DBC because of something called the angle-angle similarity postulate. So they're not congruent triangles. Obviously, this one's smaller than this one, but we can say for sure they are similar because they have all of the same angle measurements. So that means that their sides are proportional. So in step 4 here, this is what I wrote out. I said AB over DB, right? I compared this side to this one. So looking at this triangle and this triangle. So AB over DB is equal to BE over BC, right? Because their sides are proportional. That's just the definition of similar triangles, that they have proportional sides. So you're almost done from here. Take a look at this. If you simply cross multiply here, you end up with this. Last step here, you proved it. That shows that AB times BC, over here, this part times this part is equal to DB times BE. So that's it. That's the proof behind it. Makes a little bit more sense now. Anyway, you don't have to know the proof, but it's good to know where things come from at least. So this is a total logical property after all. So let's work through an example together here. All right, so here's our example. So setting this up, I just take my chord, this part times this part, so x times 8, or we could call that 8x. And that is equal to 12 times 9, which is 108. I'll write out the 12 times 9. All right, so we get 8x equals 108. Divide both sides by 8. So you could leave that as a fraction, so 108 over 8. So 4 goes into both of those, so that would simplify to 27 over 2. Or if you just divide it out, you get a pretty easy decimal. It's just 13.5. So there you go. Let's have you guys try one of these on your own now. I'm going to give you a little multiple choice problem. I've got 2 of them actually, so take a look at the first one. Pause it here, solve it yourself. I'll give you a second. And the correct answer is 16. Let's have you try another one. This one looks a little bit more challenging. Not just simply numbers, there's expressions. So pause this. I want you to try to work through it. Okay, and the correct answer is 4. Okay, we can look at this one because it's a little bit more challenging. The setup would just be x plus 8 times x plus 4 equals x times x plus 20. So if you got the correct answer and you're good, you can fast forward through this part, but I'm going to walk through it if you did not get the correct answer. Okay. All right, so my setup, like I said, would be x plus 8 times x plus 4. And that would all equal x times x plus 20. All right, so if we solve that out, obviously we'd FOIL this side. X times x is x squared, right? I've got x times 4 is 4x, and then I would do 8 times x is 8x. So that would be 12x plus 8 times 4, which is 32. All right, multiplying this out, we get x squared plus 20x. And then we simplify, which is pretty easy. I see an x squared, but it does go away because you can subtract this from both sides and it just goes to 0. So x squareds go away. Just doing this kind of quickly, you can subtract 12x from both sides. So you're left with 32 over here equals, subtracting that, you just get 8x. Divide both sides by 8, and that's how you get x equals 4. All right, let's move on to our next theorem here. Just 2 more, actually. This around. All right, take a look at this one. Now, this one is pretty wordy. Let's read through it, and then I'll explain it pretty simply. So this one says, if 2 secants, so you can see over here, I've got 2 secant lines, intersect in the exterior of a circle, then the product of the measures of one secant segment and its external secant segment is equal to the product of the measures of the other secant and its external secant segment. That is very wordy. Let me explain what it's saying. So I tried to highlight here. If you look at this, it basically shows that AC, that's the entire secant line, times the outer part, AB, is equal to, same thing on the other secant, all of AE times the outer part, AD. So when I see 2 secant lines like this intersecting on the outside, I just like to think of it as the whole thing times the outside part equals the whole thing times the outside part, just like that. So let's take a look at an example of that. Okay, it says find x. All right, so we've got 2 secant lines, so I'm going to apply this theorem here. Let's take a look at this secant line first. Doesn't matter which one, but let's look at this one. Okay, so let's apply the theorem, which says if I take the whole thing, and this is where I see a lot of errors. You guys like to look at this and say, oh, the whole thing, that's 8x. Well, careful, it's not. It's actually this part plus this part. So that would be 8 plus x, or x plus 8, whatever order you want. Okay, so I can do x plus 8, that's the whole thing, times just the outside part, so times 8. And I'm going to do the same thing over here. So that is going to equal to whole thing here, which is 10 plus 24, so 34, times just the outside part, 10. All right, Let's go ahead and multiply this out. So this is just distributing this direction. So that becomes 8x plus 64 equals 340. All right, subtract the 64. So that would be 276. And then divide by 8. You can use your calculator. It is a decimal, pretty easy one. It's 34.5. There you go. Okay, I'm going to have you guys try one of these now. So here you go. There is your problem. You can pause it, see if you get the right answer. And the correct answer is 26. All right, we'll go on from there. All right, let's look at our very last theorem for our section. Okay, again, I did a little color coordinating here. You might want to do the same. All right, so it's similar to the previous theorem with one little difference. Let's read through it first of all. So this one talks about a tangent and a secant instead of two secant lines. So it says if a tangent and a secant intersect in the exterior of a circle, so here's my tangent in red, here's my secant with this blue part on the outside, then the square of the measure of the tangent is equal to the product of the measures of the secant and its external secant segment. Again, that's wordy. Let me explain it. It's pretty easy. So if you look at our example right here, look at this side first actually. So this says JL times JM. Well, that's basically what we just did with the secant line. So it's saying outside part times the whole thing. It just said it in reverse. So the whole thing times the outside part is equal to, so really the same thing with the tangent. The whole thing times the outside part, which if you notice, the outside part is the whole thing. So that's why they just have JK squared. You're doing JK times JK. Okay, so that's the only difference right there. So let's take a look at an example.